Okay, this first video, we're going to talk about the lab on measurement. Okay, so we want to transition to the metric system. All right, so here in Brooklyn, we measure things in inches and miles and feet and yards. And the conversion we're going to be interested in here in lab is that 1 inch is going to be equal to 2.54 centimeters. Okay, so this is what we're going to use in lab. Okay, so for all the lab things, we're going to use this value. Okay, for class, when we're not doing lab stuff, and for our exams, we can use the approximation that 1 inch is approximately 2.5 centimeters. Okay, and this will allow us to be able to convert fairly rapidly. So for example, if we say 40 inches is how many centimeters? Okay, well, what we're really doing is multiplying this equation here by 40 on this side, and that means we have to multiply this side by 40. Okay, so what you do first is you multiply 40 times 2 would be 80, and then 40 times a half is 20. Okay, so 80 plus 20 should be 100 centimeters. Okay, if we play this game again, if I do 90 inches equals how many centimeters? Again, we're doing this approximation, 2.5. Okay, so 2 times 90 is 180. Half 0.5 of 90 is 45. So 180 plus 45 would be 225. Okay, so hopefully you can learn to do some of these simple transformations inside, in your head. You don't need to use a calculator, but you certainly can use a calculator. Okay, now we're going to measure things like, lab 1, we want to measure mass. Okay, mass is not the same as weight. Okay, so it's not the same as the weight of an object. Okay, keep that in mind. Okay, we'll learn about this later. Weight is actually a force, or the force due to gravity. Okay, force due to gravity. Okay, so if you're in outer space and the gravitational force is 0, then your weight is 0, but you still have the same mass. So to be very simplistic, we could say that mass is how many atoms an object has, how many particles it's made of, okay? And so even if you're in outer space, you are not massless, but weight, which is an effect of gravity, could be 0, because if there's no gravity, then you have no weight, okay? Now we're going to measure mass with 2 different devices in the lab. Okay, the first one is called the centogram. Centogram, okay? And we call them balances. I like to call them scales, but the chemists say scales are what fishes have. So we call them balances, okay? And this is going to measure mass to 0.1 grams. So 1/10 of a gram accuracy. So it's not so accurate, not so accurate, not super, super accurate, okay? Now, I just want to point out, if we have, suppose this is 0.7, excuse me, and this is 0.8, okay? If our marker somehow, when we measure the weight of something, the mass of something, if our marker comes to this point, right, then our mass, and let's say it was 23 point. Now it's going to be 0.7, okay, because it's a little past the 0.7. And now we can guess at the next decimal place. You see, we don't really know. So it looks like it's a little less than halfway. If it was halfway, it would be 0.75. So maybe I'll just say 0.74. Okay, so this last 100th place is not so accurate. Okay, but this is definitely accurate. Okay, so the centigram can measure up to the 100th or estimate up to the 100th. Okay, now there's another balance in lab, and it's called the analytic balance. Analytic balance, okay? Again, it's another way of measuring mass, okay? But the analytic balance, right, is going to measure things to this, to 0.0001 grams, okay? So that's 10, 100th, 1,000, 10,000th place, okay? So this is super, I'll say super accurate, super accurate. Okay. In fact, it's the best thing we have to measure mass in this lab, all right? So for everything we do, any measurement with the analytic balance, okay, keep this in mind, we're going to take to be the exact answer. You'll see what I mean later, exact answer or exact mass, exact answer or result for mass, result or measurement for mass, okay? So whatever we get on that analytic balance is going to be the exact answer. The centigram balance is not so accurate. Okay, so keep that in mind. Okay, all right, so I'll come back to that in a couple minutes. The second thing I want to talk about right now in terms of the lab is we're going to talk about temperature, right? So temperature and temperature scales. Oopsie, temperature scales, temp scales. Okay, let's first talk about Celsius. Okay, Celsius. Okay, Celsius, that's an S, Celsius. Okay, all right, the Celsius scale, we know, well, most of us should know that when water freezes, freezes at 0 degrees Celsius. Okay, I'm going to put a marker there. Okay, and then at 100 degrees Celsius is where water boils. Okay, now if we look at this scale and we counted all those steps between 0 and 100, I'm sorry, it's not so accurate. All right, it's clear that there's 100 steps between boiling and freezing. Or freezing and boiling, okay? That's the Celsius scale. If we go to Fahrenheit, if I spell it right, all right, Fahrenheit, all right? So we want degrees Fahrenheit, okay? Well, I'm going to try to draw something right here because it's going to be the same thing. Water freezes in Fahrenheit. I think we all know it freezes at 32 degrees Fahrenheit, okay? The question is, to be exactly equal here, I'm going to draw a dotted line across. What temperature does water boil at Fahrenheit? Well, it turns out it boils at 212 degrees Fahrenheit. Okay, if we count the number of steps between freezing and boiling on the Fahrenheit scale, count the number of steps, we would count that there's 180 steps. 180 steps. I call them steps. They're really degrees, right? So I'll put that in quotes. Okay. Now let's stop for a second. Okay. Let's use our imagination for 1 second. Imagine we have a building here, and the building has a certain height. And in that building, there's 100 steps to get to the top, 100 steps, okay? Now we have another building. It's the same height. It's the same height. But in this building, they made it 180 steps to get to the top. So 1 step or 1 degree Celsius here is not the same as 1 step or 1 degree Fahrenheit here. The Celsius steps are bigger. You see they're bigger? because it only takes 100 steps to get to the top. And here it takes 180 steps to get to the top. If it took 200 steps to get to the top, if it was 200 instead of 180, if it was 200 steps, then we'd say Celsius, which is still 100 steps, would be twice as big as the Fahrenheit steps. But since there's 180 steps of Fahrenheit, we can say this: 1 degree Celsius is equal to 1.8 degrees Fahrenheit. In other words, if you go up 1 step here, if you go up 1 step, that means you have to go up 1.8 steps here to get to the same height. Okay? So 1 degree Celsius is 1 degree Fahrenheit. Okay? And so if on a quiz or on an exam, I ask for the change in temperature, remember change in temperature, change, you can put a delta, everybody should know delta. If I say delta T, if the change in temperature is equal to, I'll just say 8 degrees Celsius. And I say, well, how many steps then? What change is that in degrees Fahrenheit? In other words, if you go up 8 steps on this side, 8 steps, if you go up 8 steps, how many steps did you have to go up in Fahrenheit? Well, 1 degree Celsius is 1.8 degrees Fahrenheit. So if I multiply this by 8 times 1 degree Celsius, it's got to be the same as 8 times 1.8 degree Fahrenheit. Okay? Well, 8 times 1 is 8, and 8 times 0.8, 8 times 8 is 64. So 8 times 0.8 is 6.4. Okay? And so 8 plus 6.4, the change would be 14.4. So if you go up 8 steps in one building in Celsius, then that means the equivalent height or equivalent number of steps would be 14.4 steps in Fahrenheit. Okay? So this is usually the type of question I'll ask on an exam, is the change in temperature. Okay? Okay, let's talk about a graduated cylinder. This is also in the lab write-up, okay? A graduated cylinder. Okay, so graduated cylinder has markings, so we can measure the volume. Okay, so we're going to measure volume. Okay, so I'll draw a terrible picture here. Okay, and there'll be markings. Okay, that's the graduated. Okay, now let's do an exaggeration 1 second. Okay, let's say that this is 6, and and I'm just picking here 6 maybe and 5. Okay, it doesn't matter. Okay, and I'm just showing you an example, and here's 5. Okay, now in between you'll see there's many little markings. Okay, and usually there's sorry, it's not that even. Okay, there's 4 markings in between. Okay, and then so if the reading, and I'll do that in a second, if the reading, in other words, if the liquid comes up to a certain point, we're going to put a liquid in here that I'm going to talk about. If the liquid, just say the liquid comes right up to here, and the question is, well, what is that reading? Okay, what is it right here? Okay, well, this is 5. Well, this is going to be 5.2. This is going to be 5.4. This is going to be 5.6. This is going to be 5.8. Okay, I think everybody could see that. So the reading, this reading will definitely be 5.4 because it's between 4 and 6. Okay, is it halfway? Well, it looks a little less than halfway. If it was halfway, it would be 5.5. Okay, so maybe it's I don't know, 5.4. Not 5. It's not 5, right? We said it's not 5.5 because it's not halfway, right? So it's going to be 4.4, maybe 8. I don't know. We could guess. Okay? I don't know. but we'd have to guess at the next one. But it's definitely a little less than 5.5. Okay. All right. So let's look at the graduated cylinder for a second and what's going to be. Okay. Here we go. If we put a liquid in, again, there's going to be markings here, which I don't care about right now. Okay. When you put a liquid in, you'll see it does something like this. Whee! I'm sorry, it's not so neat. Okay. The liquid, whatever we put in, is going to make this kind of U shape. Okay. And it's going to stick to the sides. You see, this sticking to the sides, since this is usually made of glass, and inside we have our liquid, water or whatever else we have a liquid sticking to glass. Those are two different substances. When two different substances stick together, we call that adhere or adherence. So these adhere to each other. That's two different substances. When two of the same substances stick together, we call that cohere or coherence. Okay, this is adherence. Okay. Adhere is two different substances. Coherence is two of the same substances. Okay, so usually Band-Aids say, oh, they adhere to your skin because the Band-Aid is made of plastic and your skin is made of skin. Okay, now this U shape that we see, because of this adherence, this U shape, is called the meniscus, which is also found in the knee, but this is a different use of it. Meniscus. Okay. And the question is, how do I read the volume? Do we read it from the top here, or do we read it from the bottom, or do we read it from halfway? How do we read it? And the answer is, I will show you again. Okay, we'll just focus on the meniscus here. Okay, the answer is, and this is our graduated cylinder. The answer is we read it from the bottom. So you always make your readings from the bottom of the meniscus. Okay. Not from the top, not from there. No, not from the middle. No, from the bottom. Okay. Now, how do we look at it? Well, if we stand here, and this is our eye, and if we looked up at this and tried to measure it, we would read something up here. And if we measured something from here, if we looked at it too high, we would measure this thing to be somewhere down here. So the way you need to read this is to be even or eye level. So you got to get down and read at the bottom of the meniscus exactly equal, okay? So you don't have an error. You don't want an error of perspective. Again, if you look at it from, if you're too high up, you're going to get a wrong reading because you're going to read down there. If you read it from too low, you're going to read it too high and you're going to get an error. So you have to read exactly at eye level. So this error of perspective is called parallax error. Parallax error. And we want to avoid parallax error, okay? We want to avoid this, okay? So whenever you measure something in the lab, make it eye level so you avoid parallax error, okay? Now, the purpose of the lab is to do some measurements on density. So we're going to talk about mass density for a second. Okay. The density, and we'll give it the symbol D for density, okay, is going to be defined as the mass of an object divided by the volume of the object. Okay. Now, volume, you should know, right? If we have a cube, if we have something like this, or something like this, right? And this is the width, and this is the length, and this is the height, right? And suppose the height is 2 centimeters, and suppose the length is 3 centimeters, and the width is 4 centimeters. Then the volume for this simple thing, right, is the length times the width times the height. Okay, and for this example, we have 2 centimeters times 3 centimeters times 4 centimeters. And what is that? 24. 2 times 3 times 4 is 24. Centimeters times centimeters times centimeters is centimeters cubed. So cubed, this cubed lets you know that you have a volume. Okay, so a length to the 3rd power is a volume. But not everything is a cube, so we got to figure out how to measure the volume. We'll do that in a second. Okay, so if I wrote this equation in just symbols, D equals M over V. Now, mass is going to be whatever units. We can use grams. We can use kilograms. We can use nanograms. We can use micrograms. We could use anything. Milligrams, it doesn't matter. Volume, well, it has to be a length cubed. So volume could be anything. It could be centimeters cubed, which is a milliliter. Okay. Okay, so that's a milliliter. It could be meters cubed. It could be, it doesn't matter. We don't have to stay with metric. It could be inches cubed or feet cubed. Any length cubed, right? It could be millimeters cubed. Okay, any length cubed is a volume. Okay. Now, so density is M over V. Now, remember, people are afraid of equations, right? They're afraid equations. This is math. Ugh, we hate math, right? But remember, all these things stand for are just numbers, okay? So, for example, if I say 6 equals 30 divided by 5, well, 6 would be the density, right? I'm not putting units in now. The mass would be this 30, and the V would be 5. Okay, and clearly, if we multiplied both sides by 5, right, then 5 divided by 5 goes out, and 5 times 6, we end up with 30 equals 30, or 5 times 6 equals 30. See, so that's just algebra. So here in symbols, if we multiply both sides by V, instead of 5, I just put V, multiply by V, okay? Then the V's go out, and I have V times D is equal to M, or 5 times 6 is 30. It doesn't matter, okay? So mass can be written as the density. I could put D times V, okay? So you don't think it's some kind of disease, okay? So you can play this game by substituting. So we're going to come back to this, okay? Now, what we want to do is we want to get the math. We want to do some things with copper, okay? We're going to have a little piece of copper like this. We don't know the mass, okay? Okay, well, what could we do? Well, of course, we're going to put it on a balance, okay? And I'll talk about that in a second. My other thing is, how do we get the volume of this? Well, if we know math, we can measure the length and width, size of the top, the area on the top, the length here, we can do some things. But we want to get the volume of this little cylinder. Okay, so that's what we're going to talk about right now. But I want you to put this on the side. They give us in the lab the density of copper. Ooh, isn't that nice? The density of copper. And it's on page 1 or 2 of the lab write-up. Density of copper, D, is equal to, what is it, 8.97 or something like that. I think 8.96, I think. 8.96 grams as the mass over the volume per milliliter. Okay, so this is a given, so we know this number. Okay, we know this number. Okay, so let's see. How do we get the volume? How do we calculate that? How do we get the volume? Well, I'm sure a lot of you already know this. What we'll do is we're going to take a graduated cylinder. I'll make it nice and big. How's this? This is big. And now I'm going to put some water in here. We're going to put some water in there. And if I was actually in lab, if I'm not online, what I would do is I'd use a squeeze bottle so I can make it very accurate. So remember, there's the meniscus. And let's say that I make it so that this thing comes, I'm going to make an easy number, exactly at 10 milliliters. Okay, so there's the water. So what? Now what we want to do is we're going to put the copper cylinder in. Okay, now what happens when you put copper cylinder in water is, obviously, the water is going to rise. By how much? By the volume of the copper cylinder. Okay, so I'm going to redraw this, and then I'm going to redraw this meniscus, and now on the bottom, that's our piece of copper. Okay, copper. Okay, now let's say the meniscus comes right up to here, and let's just say I'm making this up, 12.6 milliliters. Okay, so now we know what the volume of the copper is. The V volume of the copper is going to be the volume with the copper in it, 12.6 milliliters, and then subtract the value without the copper, right? 10 milliliters. And so the volume of the copper is equal to 2.6 milliliters. See how easy? Now we know the volume of the copper. Okay. Now, if we know the volume of the copper, remember density is mass over the volume. Okay. So the mass, remember, is the volume or the density times the volume. Okay, so we know the density of copper. We know the volume of copper. Remember, the density of copper was 8.96 grams per milliliter. Okay. Oops. Okay, make sure the pen's working. Okay. No, it's not working. Okay. Let's do this, and then let's go this. Okay. Okay, 10.6 milliliters. 8.96 grams per milliliter. And now we're going to multiply by the volume, which we just got, times 2.6 milliliters. Okay, now the milliliters go out, and I just get grams, which I want, right? That's the units of mass. So if I take out my little calculator, and I multiply 2.6 times 8.96, we end up with 23.296. Okay, now remember, oh, this is pretty bad, but okay. Oopsie. This is 2 significant figures. This is 3 significant figures. So my answer must only be to 2 significant figures. So if I round this to 2 significant figures, and this would be grams, would be 23.3 grams. Okay. And so this, in the lab write-up, this is called M experimental number 1. Okay. So this is the way we got the mass using knowing the density and then getting the volume with the water. Okay. Now, the exact result that we're going to take, remember, exact result will be when we take our little piece of copper. That's our copper. And we're going to put it on the analytic balance. Okay. Now remember, this is our exact result. Okay. And let's make believe. I'm going to make believe. Let's say our result is 24.183 grams. I don't know, 2 grams. I don't know, whatever. Okay. This is what we get on the analytic. I'm making this up. Okay. So this is going to be our M exact. Okay. All right. So what did I have? 24.1832. 24.1832. All right. So now what do we do? All right. Now remember, I want you to pay attention, because those of you who go to lab, before we put before we do the experiment up here where we put it in the water, right? We want to get the mass before we put it in water. We put copper in water. Okay. So before you do the copper in the water, you got to put it on the balance, the centogram and the analytic. Why? Well, obviously, because if it's wet, if this is a little bit wet, you'll get a different value for the mass, right? The mass will be different. So we don't want to have a wet mass. Okay, so we're going to put all our mass on the analytic balance and the centigram balance before we wet it, before we put it in the water to get the volume. All right, so now we have the centogram. Centogram. Okay, so we're going to put it on that balance, and let's say, and I think they might call this mass experimental number 2. Okay, let's say we put it on the centigram, and I'm making this up. Okay, so suppose we get 23.84 grams. Okay, and that's what we get with the centigram. Now remember, our exact result, we said was 24.1832 grams. So this is not right. It's a little off. So there's some error. Okay, now if I go back up, remember when we did with the water, we got just 23.3 grams. Okay, so remember when we put it in the water, when we put the copper in the water, M experimental number 1, if I look above, was what? 23.3 grams. But if you look, 23.3 grams is different than the exact result. See, our exact result. So there's also some error. The question is, how much error? Okay, so now we're going to calculate percent error. How much error? How much are we off? Okay, 10%, 6%, 28%. How can we figure out how much error? Sorry, that's an E for error. Okay, well, here's a formula given to us in the lab write-up. Okay, percent error for any quantity, we'll call it X for now, is given by, okay, X, whatever the X is, the exact result, minus, and it doesn't matter which one we take minus what we measure, the value we measured. We're going to divide by X exact. And we're going to multiply this whole thing by 100%, so we get a percentage. Okay, so for example, 2 divided by 10, we know is 0.2. 2 divided by 10 times 100% is 0.2 times 100% is 20%. Okay, so we convert fractions into this percentage. Okay, now also we're going to put something here. I'm going to put these bars like this line here and line here. This means absolute value. Absolute value is always positive. Okay, I'm going to write that here. Absolute value is always positive. So your percent error is always positive. Absolute value is always positive. Positive. So for example, if we have the absolute value of minus 9 is equal to 9. The absolute value of minus 0.23 is equal to 0.2. Oops, my pen went out again. Is equal to 0.23. No minus sign, okay? So the absolute value of 6 is 6, okay? So it's always a positive number, all right? So we want to calculate the percent error, all right? So let's do the percent error for mass number 1. Mass experimental number 1, okay? Okay, so here's the percent error equals. Now remember, the exact value for the mass was 24.1832, okay? And that's grams. Now we're going to subtract mass experimental number 1. What was mass experimental number 1? I forgot already. 23.3 grams. Okay, take the absolute value, even though this will be a positive, but it doesn't matter. And we're going to divide by the exact value. Well, that was 24.1832 grams. And then we're going to multiply this whole thing by 100%. Okay, now notice we have grams and grams and grams. Grams go out because the percent error is a number. It's just a number. It does not have units. So percent error, I'm going to write that here. Percent error is always positive, and has no units. It's just a number. 23%, 17%, 80% has no units, okay? No units. So these units cancel out. The grams on top divided by grams in the bottom go out, okay? So now if I take my calculator, let me see if I can get this correct without making too many errors. All right, so let me take my calculator out and take 24.183. Okay, so what do we have? We have 24.1832. I'm going to subtract 23.3. Right? Now I'm going to divide by 24.1832. And now I'm going to multiply by 100%. And what I end up with is 3.65%. So that's my error number one. So this is percent error for mass experimental number one. Okay, so now we do once more, and I'll finish it off, percent error for M experimental number two, right? Mass experimental number two. Oh, I forgot what it was already. Mass experimental number two, where is it? Where is it? Where is it? 23.84. grams. Okay, so here's the percent error. We're going to take the exact result. Remember, it was 24.1832. And I could put grams in, even though it'll cancel out. Now I'm going to subtract my measured value, which is M experimental number two. So this is minus 23.84 grams. And again, we could take its absolute value, but this will be positive. And now we're going to divide by our exact result, 24.1832 grams. Once again, these grams go out, no units, no units. All right, and we have to multiply by 100%. Okay, and again, I take my trusty calculator, I take 24.1832. Now I'm going to subtract 23.84. Okay, and now I'm going to divide by the exact result, 24.1832. And then I'm going to multiply by 100%. And I end up with 1.419. So I'm going to put one, oopsie, again, my pen went out. Okay, so I'm going to, so this is equal to 1.419. I'll just make it 1.42%. So this is my percent error. Okay, and we're all happy. That's a really good error. And 3.56, I'm also very happy with that result. Okay, and that's lab number one. Again, there'll be certain conversions where you measure the length from the tip of your nose to the end of your finger, and you want to convert that from inches to centimeters or centimeters to inches. And so it's just practice, okay? But other than that, this is the gist of the whole experiment. And I hope it's good. Okay? That's good.